Good afternoon. I'm Ms. Mikesell, and this podcast is going to focus on the colligative properties of a solution. Our EQ for this podcast is how does the concentration of a solution affect the properties of the solution? Colligative properties means predictable physical property changes that occur in solutions. Colligative properties depend on the number of solute particles present in the solution, i.e., the concentration or molarity of the solution. It does not depend on the type of solute particles. So it does not matter if we have ionic or covalent particles in solution. The amount of particles determines how the physical properties change, not the type of particles. In other words, a saltwater solution and a sugar water solution would have the same result on the physical properties based on their concentration or molarity. So if we examine what's happening with colligative properties, how would the addition of a solute affect the freezing point of a solution? And in our image, we can see that when something is solid, it's crystalline in structure. All of those molecules are very orderly in their arrangement. In liquid, things are mobile and moving around a little bit more. And as a vapor, those particles are much further apart. If we consider what happens in a liquid when we add a solute into the solution, we can consider the black particles the solute. And what happens is the solute disrupts the molecules, and that slows the molecules down from freezing because it's putting obstacles in between them. And when a molecule freezes, it freezes in a nice crystalline orderly arrangement. And so that disruption of the molecules, slowing them down, lowers the temperature by which they freeze at. We call that the freezing point depression. The addition of a solute makes the liquid state less organized, and thus the solute ions or molecules are moving about randomly. The freezing point will be lowered with the addition of the solute, and this is a direct proportional relationship. As the concentration increases, the freezing point depression would increase proportionally. So let's watch a video that goes over freezing point depression.
Life's not always sweet. Time for a teachable moment.
Yep, and this one is about something called freezing point depression. I'll let the owners take it from here. Nick?
Freezing point depression is very important as far as creating pops or any frozen dessert for that matter. It can make the texture better or worse, meaning softer or more firm.
And exactly what is freezing point depression?
Freezing point depression is when you lower the temperature at which something will freeze. You take that into consideration because you want it to not be quite as cold. So you add salt. We add salt into everything that we make to depress the freezing point a little bit. Sugars can do that too. There's a lot of different ways you can do it.
That's true, but it helps to understand that heat is the motion of molecules. More heat energy, more molecule movement. So the colder water gets, the more those molecules slow down. At 32 degrees, those molecules, which are all the same size and shape, line up nice and neatly side by side, forming crystals. This is where water goes from a liquid to a solid, and it's technically known as phase change. But if you add a solute, like salt or sugar, to the solvent, those water molecules can't line up as neatly. So it takes lower temperatures, freezing point depression, in order to slow the water molecules down enough to form crystals. Of course, they do this naturally at King of Pops, because for them, it's all about the flavor.
So our next question would be, how will the boiling point change with the addition of a solute? And as we look at the animation on the left, we can see it's pure water. The animation on the right is showing a 1 molar sodium chloride, i.e. saltwater solution. Note the sodium ions are blue and the chlorine ions are green in the water. So hopefully what you're thinking is, those sodium and chlorine ions are disrupting the water molecules in solution, And if those water molecules are trying to evaporate off the top of the solution, then the sodium and chloride are going to be preventing them from doing so as easily because of their disruptive presence. Yeah, the boiling point's going to increase with the addition of a solute. Pure water has a boiling point of 100 degrees Celsius, whereas a 1 molar saltwater solution has a boiling point of 101 degrees Celsius. So this is known as boiling point elevation. The boiling point is raised with the addition of a solute. The addition of a solute affects the vapor pressure and slows the rate of evaporation. It is again a direct proportional relationship. As concentration increases, the boiling point would increase. So we can see that as a solution boils, if the solute is non-volatile, in other words, it doesn't evaporate, then only the pure solvent enters the vapor phase. The solute stays behind. This is the meaning of the word non-volatile. However, the consequences is that as the solution becomes more concentrated, its boiling point increases. Thus, if you plot the temperature change of a pure substance boiling versus time, the line's going to stay flat. The boiling point is constant. However, with a solution, the line tends to drift upward as the solution becomes more and more concentrated as the water evaporates off and more of the solute is left behind, further disrupting the molecules that remain. Wow, hopefully you're looking at this triple point graph of solutions and having flashbacks back to August in our kinetic molecular theory unit with gases. We can see that the triple point shows us the temperature and pressure at which each substance is a solid, liquid, or a gas. And we can see that that triple point and the conditions at which the substance is solid, liquid, or gas decreases with the addition of solute. So we can see the blue line shows the shift in that. At a vapor pressure of 1 atmosphere as the reference point, if the pressure stays constant, the temperature at which the phase change occurs is altered by the addition of the solute. So if we go to a reference point of 1 atmosphere, we can see that this used to be our transition, our melting point between a solid and a liquid, known as the melting or freezing point, and that's going to decrease with the addition of a solute. It's going to lower, and we can see the same thing over here, the boiling point elevation, because at 1 atmosphere of pressure, our boiling point used to be right here, and with the addition of a solute, it increases and goes in this direction. So we can see our boiling point elevation and our freezing point depression. Some real-life examples of colligative properties is things like magnesium chloride. Road salting takes advantage of colligative properties to lower the freezing point of the ice it's placed on. Lowering the freezing point allows street ice to melt at lower temperatures, preventing the accumulation of dangerous, slippery ice. Commonly, they use sodium chloride to depress the freezing point of water to about -21 degrees Celsius. If the road surface temperature is lower, sodium chloride becomes ineffective and other salts are used, such as calcium chloride, magnesium chloride, or a mixture of several salts. A second example would be antifreeze, or methanol that you put in your car. The phenomenon of freezing point depression has practical uses. The radiator fluid in your automobile is a mixture of water and ethylene glycol. As a result of the freezing point depression, radiators do not freeze in the winter unless it's extremely cold, -30 to 40 degrees Celsius. You may expect antifreeze to protect a car from overheating as well due to boiling point elevation. This doesn't really work though, as antifreeze has a reduced ability to absorb heat compared to water. In other words, its specific heat is not as good. So you're about to do 2 labs. The first lab you're going to do is use coffee creamers, different flavored coffee creamers, to make ice cream. And the key to successfully making ice cream using colligative properties is to make sure that the freezing point is lower than 0 degrees Celsius, and we need to sustain it there for several minutes. So you want to make sure that you keep your coffee creamer at a temperature of about -8 degrees Celsius for several minutes so that you get a nice creamy ice cream flavor. And then you're going to do this demo with everybody that's doing this enrichment lab at the end of class, but we'll give you a sneak peek at what you should see when you do the seltzer water demo. You're going to want to remove the label for better viewing and add the club soda or seltzer water into a saltwater ice bath. Again, for at least 10 minutes until the temperature is -8 degrees Celsius. And then once you remove it from the salt ice bath, you'll very quickly uncap it, and the soda will be in the liquid state. But as you open the bottle, that carbonation or the carbon dioxide gas is escaping. Carbon dioxide gas is a solute, so you're decreasing the amount of solute in solution, which will allow the substance to now freeze at the temperature that it's at. So that'll be pretty cool. Let's watch this final video to see that happen. And you can do this as you start to lower the freezing point on your 2 labs.
You're as cold as ice. You're willing to sacrifice our love. You never take advice. Someday you'll pay the price. I know. I've seen it before. It happens all the time. You're closing the door. You leave the world behind. You're begging for gold. You're going away. A fortune and feelings. But someday you'll pay.